In 1972, the German government broke ground on a nuclear reactor near a small medieval town on the Lower Rhine, a project that was supposed to cost somewhere between $150 million and $200 million, but ended up costing $4 billion, took 13 years to build, employed thousands of engineers across 3 countries, and never generated a single watt of electricity. Today, if you visit that same site, you will find a 25-ton swing ride spinning inside the cooling tower, a climbing wall bolted to its outer concrete shell, and a mural of a mountain range painted across the face of a structure originally designed to vent steam from a plutonium breeder reactor. The complex has 4 restaurants, 8 bars, 6 hotels, and more than 40 amusement rides, and it draws 600,000 visitors a year to a town of 14,000 people. That is not the interesting part, though. The interesting part is that nearly every physical constraint the original reactor imposed on this site is still shaping what happens there more than 30 years after the project was canceled. The concrete is still dictating the layout. The cooling tower is still the tallest thing for miles. The road network built to haul reactor components still routes every visitor through the same entrance. And the fact that this reactor was never loaded with nuclear fuel is the single reason any of this was legally possible at all. That is the pattern this video is really about. Not the quirky amusement park, but the deeper thing underneath it. When a structure built for one purpose fails catastrophically, the physical decisions locked into it do not just disappear. They become the constraints the next use has to solve, work around, or inherit whole. And the story of what happened in Kalkar shows you exactly how that process plays out, from the first protest march to the last roller coaster bolt. To understand why this site works the way it does now, you have got to understand what it was built to do and why that mattered so much at the time. In the early 70s, West Germany had a problem. The 1973 oil crisis had just exposed how dependent Europe was on imported energy, and Germany had almost no domestic oil or natural gas to speak of. What it did have was a limited supply of uranium and a deep bench of nuclear engineers, so the government, along with Belgium and the Netherlands, commissioned a Siemens subsidiary to build a fast breeder reactor. This was not a standard nuclear plant. A fast breeder uses plutonium as fuel and liquid sodium as coolant, and the key selling point is that it actually creates more fissile material than it consumes, meaning one of these reactors could, in theory, stretch Germany's small uranium reserves for decades. Construction started at the end of 1972. The site they chose was a flat stretch of farmland near the Rhine, just outside a town called Kalkar, about an hour north of Dusseldorf, and practically on the Dutch border. The location made sense for cooling water access and transport logistics. The reactor was designated SNR 300 and rated to produce 327 megawatts of electrical power. The total complex would eventually cover 55 hectares, roughly 80 football fields of reinforced concrete, piping, and containment structures, all anchored into the Rhine floodplain. And this is where the lock-in begins, because a fast breeder reactor is not just another power plant. It is an entirely different kind of engineering commitment. The sodium coolant cannot be allowed to come into contact with water or air because sodium explodes on contact with water and burns in open air. So the entire primary cooling loop had to be sealed inside multiple layers of containment that no conventional plant would need. The reactor vessel sat inside a concrete housing designed to survive a theoretical sodium fire and contain a potential breach. The cooling tower, a natural draft hyperboloid shell rising nearly 60 meters above the Rhine floodplain, had to be sized for a thermal output of 762 megawatts, even though the electrical output was only 327. That is the thermal inefficiency of a fast breeder. You build cooling infrastructure for more than twice the power you actually deliver to the grid. And every one of these engineering requirements created physical structures that would still be standing decades later, long after anyone stopped caring about plutonium. The first sign that the project was in real trouble came in 1977, when 40,000 people marched through the streets of Kalkar in what was then the largest anti-nuclear demonstration Germany had ever seen. police closed autobahns across northern Germany and checked the identities of nearly 150,000 people in a single operation. The protesters were not just local, they were part of a growing national movement that had already shut down a reactor site in the southwest and was gaining political traction fast. 2 years later, in March 1979, 3 Mile Island suffered a partial meltdown in Pennsylvania, and the German anti-nuclear movement shifted from protest to policy. A commission of the federal parliament ordered a full safety review of SNR 300. Construction stopped for 4 years while engineers redesigned the safety systems to account for the specific risks of a sodium-cooled breeder. The cost overruns accelerated. The original budget of $150 million to $200 million was already a distant memory by this point, and by the time construction resumed, the project had burned through billions. In 1985, the reactor was finally completed. 13 years of construction and 7 billion Deutschmarks were spent, equivalent to roughly $4 billion at the time, or about $9 billion in today's money. The sodium coolant was pumped into the primary loop, and it had to be kept hot with electric heating elements 24 hours a day, because if it cooled below a certain temperature, it would solidify inside the pipes. Just keeping the completed but unused reactor in standby mode cost over 5 million euros a month. And the reactor was ready to go. All the technical approvals were in place, and the Federal Safety Commission had given its sign-off. But the state government of North Rhine-Westphalia, which had legal authority over nuclear licensing, refused to issue the final operating permit. An election was coming in January of 1987, and neither the state nor the federal government wanted to be the one to flip the switch on a plutonium breeder reactor while voters were paying attention. Then, in April 1986, Chernobyl happened. The explosion at the Soviet reactor sent a plume of radioactive fallout across northern Europe, and in West Germany, authorities ordered crops destroyed and playgrounds dug up. The federal government created an entirely new Ministry of the Environment, specifically in response to the disaster. Public opinion didn't just shift against nuclear power, it calcified. The SNR 300, already politically toxic before Chernobyl, became completely untouchable. For the next 5 years, the reactor sat complete but empty, hemorrhaging 5 million euros a month in standby costs, while politicians at every level of government tried to figure out who would be the one to officially pull the plug. On March 21, 1991, the federal government formally canceled the project. The demolition of removable components cost another 75 million euros. The reactor core was transferred to storage, and the breeder fuel that had already been purchased was shipped to France and mixed into fuel rods for French nuclear plants. The SNR 300 had consumed the equivalent of roughly $9 billion in today's money and produced exactly nothing. If you find this interesting, consider subscribing to the channel. We cover the kind of details most people walk past without noticing. Enjoy. Now, what was left behind was a problem with a very specific shape: 55 hectares of industrial infrastructure on the Rhine floodplain, designed to contain a sodium-cooled nuclear reaction, with concrete walls thick enough to survive a theoretical meltdown, cooling systems designed for thermal loads that never arrived, and a road network built to handle the transport of reactor fuel assemblies. All of it structurally intact, all of it useless for its intended purpose. And critically, because no nuclear fuel had ever been loaded, none of it was radioactively contaminated. That last detail is the hinge. The entire second life of this site swings on. If the reactor had operated for even a single fuel cycle, the containment structures, the cooling tower, the piping, all of it would have required decontamination before any repurposing could happen. And in most cases, that means decades of controlled demolition. The fact that the SNR 300 was canceled before fueling is the only reason the site could legally be sold to a private buyer at all. In 1995, the entire complex was put up for auction via a newspaper advertisement, and a Dutch entrepreneur named Henny van der Most, who had built a career buying abandoned industrial properties and converting them into leisure businesses, purchased the site for €2.5 million. He had previously turned a defunct textile factory into a swimming complex and a shuttered hospital into a hotel, so a $4 billion nuclear reactor that had never been switched on was, in his view, just a bigger version of the same opportunity. But the conversion was not straightforward, and the reasons all trace back to the original engineering. The cooling tower, for instance, the most recognizable structure on the site, is a natural hyperboloid shell, tapered at the base, wide in the middle, open at the top, with an interior volume that is enormous, roughly 58 meters from floor to rim. That geometry was designed to create a convective draft for cooling steam that never existed, but it also means the interior has a natural echo chamber effect and a massive unobstructed vertical space, which is why it now houses a 58-meter swing ride that weighs 25 tons and protrudes above the rim of the tower. The exterior concrete surface, curved and rough enough to accept anchors, supports a climbing wall. The tower's shape, dictated entirely by thermodynamic requirements for a reactor that never ran, became the signature attraction of a family amusement park. The reactor containment building itself poses a different kind of constraint. The walls are too thick and too heavily reinforced to demolish economically, so it remains housing a museum exhibit about the reactor's history. The administrative buildings designed for shift engineers and security personnel became hotel rooms. The site's internal road network, originally laid out for heavy transport vehicles carrying fuel assemblies and sodium casks, now routes minivans and tour buses through the same security checkpoints, repurposed as ticket booths. And about 2/3 of the site's buildings remain empty, because the structures were so purpose-built for reactor operations that no obvious second use has presented itself even after 3 decades. The park, which opened in 2001 after several years of gradual conversion, now draws around 600,000 visitors a year, roughly 42 times the population of the town it sits next to. It employs 550 people in peak season, making it one of the largest employers in the district, and the all-inclusive ticket covers every ride, every meal, every drink. The park draws them year after year. The economics work because the infrastructure was already built at public expense on a scale no amusement park developer could ever justify from scratch. A private developer did not pay for those containment walls, the cooling tower, or the road network connecting the site to the Autobahn. German, Belgian, and Dutch taxpayers did, over 13 years of construction, for a purpose the structure never served. This site is essentially public infrastructure. The amusement park is subsidized by a $4 billion nuclear failure. And this is the pattern worth naming. When a structure this large fails, the physical decisions embedded in it do not reset. They persist. The concrete cures, the road grades set, the utility connections lock into the municipal grid, and every future use of that site has to negotiate with the geometry of the original failure. The cooling tower cannot be shortened, the containment walls cannot be thinned, and the road layout cannot be regraded without tearing up the entire foundation. So the amusement park does not replace the reactor, it inhabits the reactor skeleton. These constraints feel permanent. That is what makes Kalkar different from a simple building repurposing story. The original purpose was never fulfilled, but the original constraints were built to full specification, so the site is simultaneously brand new and permanently shaped by decisions made in 1972. Every ride placement, every hotel conversion, every parking lot is a negotiation with engineering choices that were made for a sodium-cooled fast breeder reactor and that now serve a carousel. The influence extends well beyond the property line. Germany's entire nuclear phase-out, which formally concluded on April 15, 2023, when the last 3 operating reactors were disconnected from the grid, was shaped in part by the political fallout of projects exactly like this one. The SNR 300 became a national symbol of nuclear cost overruns and broken promises years before Chernobyl even happened. The 40,000 marchers in Kalkar in 1977 helped build the political infrastructure that produced the Green Party, which entered the federal parliament in 1983, formed its first governing coalition in 1998, and immediately began negotiating the nuclear phase-out that became law in 2002. That law gave every reactor in Germany a fixed lifetime of 32 years and banned replacements. The reactor never generated electricity, but it generated a political movement that rewired an entire country's energy policy. By 1990, nuclear power produced about a quarter of Germany's electricity. By the time the final 3 plants shut down in 2023, that share had been systematically zeroed out over 2 decades. 17 commercial reactors closed, one by one, each leaving behind its own version of the same physical inheritance problem. Cooling towers that cannot be cheaply demolished, containment buildings with walls too thick to repurpose, waste storage sites that will require monitoring for generations. The reactor at Kalkar was just the first in the sequence, the one that failed before the fuel was loaded, which made its physical afterlife the most absurd and the most visible. The next time you see a structure that obviously was not built for what it is doing now, do not ask only what it became. Ask what it was built to do and look for the places where the original engineering is still calling the shots. The shape of failure is permanent. Everything that comes after is just furniture. If you enjoyed this deep dive and would like to see more, comment your ideas down below.